See, I'm looking at the navigation here for the reverse, and as I turn it, you see how it moves and it's mapping out the projection of my path of the vehicle when I turn right and left. Well, now take this system and put it in the front wheels, meaning mapping out the path of how the car is going to go in the front, and now add that into the sensors. And now, if you can see the wheels of the other car with shape recognition cameras right inside the hood, and they would identify the wheels of the other vehicle, they can actually predict where the other vehicle is headed compared to where you're headed. So where you're headed is based on the projection of the wheels, right? Well, where they're headed is based on their projection of the wheels. And it can do a calculation, especially for impact and collision avoidance. It can calculate exactly the path of that car compared to where your vehicle is by looking at the front tires. And then obviously they can calculate on rear impact with a rear camera looking at the car coming towards you, shape recognition cameras, and they have night vision and infrared, but it would have to identify the rubber. And with infrared, the rubber is at a different heat on the tire. It has a total different thermal dynamics than the lights and the metal. So even with infrared, you would be able to recognize the tires. And so you could see the movement of the tires with your front cameras of the vehicle heading towards you. And you can spot the movement of the vehicles in front of you. Even if you're behind them and it's a rear end thing, it can actually, with the side sensors, interacting with the front, anticipating the sides left and right, it can tell you if vehicles are on the side of you, left and right. And it can have the terrain sensing. And it can tell you, now see, you need the ones that with the ground penetrating radar. It'll have a surface density. So you have to know the difference between asphalt and concrete. And then it would have to have image recognition to see the lines and everything, image and color recognition to see the lines on the highway and recognize green, like over here, green, and recognize the curb. This is shape recognition. It would recognize the curb. See the curb, how it curves and goes up? It would recognize that as a curb, the shape recognition. The shape recognition would recognize that as a sidewalk. Truly, the curb, look how a curb is featured. It doesn't have a lot of room, it's thin, and so the shape recognition would recognize as a curb, the shape recognition, the circular, and then with density, oh yeah, density recognition, right? The ground pounding or penetrating, giving you density, they would recognize that as a man cover. Truly. And so they can, sewer covers and everything else, they can recognize if the sewer cover's there or not. Todd, somebody stole the sewer cover, and he was biking down the street of Chicago, and he almost went in the hole because somebody stole the sewer cover. That goes into a whole different things. I believe there should be locks. We put a hex lock on fire hydrants. I believe all those covers that go into the ground should actually have a lock in them as well. You can't just take off the sewer cover. You have to have a special key to unlock the sewer cover. The sewer cover locks in, and then you have to get locking out. And what the city can do is put sensors in the sewer covers. Oh yeah, they can connect through their system a Bluetooth that feeds up, and it tells you if somebody opened a sewer cover Or if a sewer cover is locked, it tells if it's unlocked or locked. And so now you can identify whether things are locked or unlocked. And they put the little battery in it, and now they last for 50 years. The nuclear battery lasts for 50 years. And then if you put a backup battery, 2 nuclear batteries, that sewer cover lock will last for 100 years. You put 4 nuclear batteries, and they're really small, that sewer cover system will last for 200 years. 200 years. So when you put it in, it will feed you out information. Like you're putting things in a bridge, and it's feeding into a, how do you say this? Fiber optic. So you have sensors. It has a sender, and then you have a receiver, and then it goes into a fiber optics, and then the bridge has a brain, and it has a fiber optics, and it has sensors all along it, and those sensors send out, and it has the receivers. The sensors sense, and the receivers receive, and they send back, just like the brain. You have these synapses, you have the sending and the receiving side, and so you have a fiber optics that you can put into a bridge, and it will sense and receive. And what do you use? Ground penetrating radar on the bridge. Ground penetrating radar in the building. What is it doing? It's sensing the strength of the structure. And so you have an earthquake, and the building is sensing each floor and its movement, and it's sensing if the steel is degrading, if the concrete is degrading. It's watching the breakdown of it. It can tell the density. And so now you can see, and now the building, through its neural network, and it's a neural network, it can adjust each floor's tension. Yes, each floor has tensioners. You have dampeners and tensioners. And then each floor of the building, the tensioners would tighten up or loosen up to give the building more support. That's like the cable bridges. You can pull tighter on the cable or loosen the cable for when an earthquake is coming. Or hitting. So the bridge can control sway, it can control absorption, and it's loosening or tightening through the tensioners. It's adjusting the cable to absorb and offset the impact. But you need these sensors that can see the strength of the cable, because if the cables start deteriorating, you have to take tension off of the cable, or the cable will snap. So the tensioners can tell you the cable is weakening. Not the tensioners, but the ground penetrating. It's a density scanner. And it's put into the system, the density scanner, and then it can tell you the density of the structure. And you put these little sensors, and they send out and they read the density of the structure, like a building, a skyrise. Each floor, it reads the density of the steel. Like in 9/11, the building collapsed. It would have adjusted the building. Truly, it would have adjusted the systems based on, they would have seen the scanners would have seen the steel weakening, and then would have adjusted the structure to offset the weakening of the structure, the internals, truly pulling and loosening and readjusting the building to offset for that area of weakness, preventing the building from collapsing. And then this is where the sensors are working with the fire alarm system, the sprinkler system in that. Now this is where you need robotic sprinkler systems. Oh, you need robotic firefighters. So the sprinkler pipes get cut. You have to have robotic systems that can make up for that. So each floor would have its own little firefighting machine. Truly, firefighting machine. And so it would have so much liquid nitrogen, truly liquid nitrogen or liquid helium. So you don't need a lot of it. You can't have water in that. It would need a lot of it to put out a fire. But if it had liquid helium or liquid nitrogen or liquid hydrogen, helium I think would be better. Actually, liquid nitrogen is better. But because you don't want anything that's explosive. So dry ice like. So you would take it and you would spray it with a dry ice system, this robotic firefighter. So it can put out huge fires, and you know how big the floor is, and then you know how much capacity it needs, and then the robotic firefighter comes out and it addresses it. It's backup or can work in tandem with the sprinkler system, the robotic firefighter. And then it goes out and it uses liquid nitrogen, dry ice kinda, and it sprays it out on the fire. And obviously this thing is incredibly heat resistant, so it can go in, this design thousands of degrees of temperature and go in right there. And you need this at a nuclear power plant. A robotic system that can go into the rods, into the power plant, just a robot. And the robot has liquid helium, I think it's the coldest, and it goes up to the rods and it just sprays the rods with liquid helium, cooling down the nuclear rods. A robot filled with liquid helium, and it can make its way through. This is where driverless technology, you don't understand. Driverless technology is perfecting robots and robots' ability to move in the environment. You're making a car a robot, but what it's doing is taking a car, putting it on the road, and you have birds in the road, and it needs to sense birds, and it needs to sense animals, and it needs to sense deer. You don't want it hitting a bird. You don't want it, but it sees the vehicles around it and everything, so it can make a choice. And sometimes it has to make a choice to kill the animal, because the car in back of it and everything else will cause an accident. So then the animal perishes. But if it's a deer, it might calculate, or like in Alaska, a moose, then it might calculate, don't hit moose, moose kill you, take rear impact. So it hits the brakes and it misses the moose and allows the car in back to slam into them. Truly. It has to make that choice. You hit a moose, and I've heard that people hit mooses and dying in Alaska. So you don't want to hit a moose. It's way bigger than a deer. And then that's why they have cattle guards and that. If you hit a cow, again, it's way bigger than a deer. So again, it has to make these choices with life forms for preservation of life. So it's a trade-off. But you can have these things. You can even use robots in a zoo that can suppress an animal. Truly. If lions and tigers or bears or elephants and the caretaker is in danger, you can even use drone submarines in the shed aquarium. And if a shark's coming near, the drone can ram the shark. Truly, can ram and tase the shark. Truly, the drones can protect the people that work for the shed, and so they have protection drones, and it makes sure that the animals don't come too close, the aquatic life doesn't come too close. And it can use shape recognition to tell the difference, what is allowed and what is not allowed. And if a dolphin is coming with ramming speed, then it would cut off the dolphin. If the dolphin is coming slower and more friendly, then it won't cut off the dolphin. But if the dolphin is coming aggressive, then it will hit the dolphin. Truly, it will use electronics in that, send out and try to avoid. But if need be, ram the dolphin. They take hits and give hits. So these little underwater drones would protect them. Now they can use them with divers that are diving in deep sea platforms, these underwater drone submersibles, as protection drones. And they would scan around, constantly scanning as the diver's working on the platform, making sure that the diver doesn't get attacked by a great white or any other things. Or like in Australia, saltwater crocodiles can go 50 miles or greater out into the ocean, and it would detect it and it would address the saltwater crocodile. Now you might need multiple, but these underwater drones, and they can be underwater and surface like a sub. Sub can go under and it can stay at surface, and it moves with the diver, protecting the diver. And so now you can do this underwater work and you don't have to worry about being attacked because you have protection submarine drones. And they have the right tool set to address any underwater threat. And so it would just stay there and monitor the area around the diver. And if the diver's ever at threat, it would address the threat immediately. It would alert the diver and address the threat. So moving into these things, you can move into a whole new world of betterness. But like I showed you, you put this in to a car with its sensors, and then infrared can tell something is there or not. Like when I was turning in my Honda, it was braking and the car wasn't moving, but the radar was hitting the car, thinking I was in a collide with it, but I was turning. It shouldn't have been self-braking. It was a self-braking system that was braking in turns that should have never broke or hit the brakes. I was turning. So again, that should have never happened. So the self-braking system wasn't designed, it doesn't navigate with the wheels. So as I turn the wheel, my path changes. I'm not heading towards that car. And if the system can recognize their wheels, they know where that car is heading. And the system already knows if the car is moving or not and how fast the vehicle is moving. So it can predict side impacts and everything else. So you have side sensors as well. So the side sensors would speed up the car. Like when I got T-boned, the side sensor has the sensor of the cars in front of me and around me, and it would have made an evasive maneuver by accelerating, right? Or it would have went around the car in front of me because the sensors are on the outside of the mirrors. Oh yeah, they have to be on the outside of the mirrors, not only forward looking, but looking horizontal from the side, going all the way out horizontally, and then from the mirror looking back. Why the mirrors? They extend outside the car's body. So they can see around things that you can't see because you're within the vehicle. So the sensors would be in the mirrors. They get this further distance, and so they can see around the back. The sensors, yeah, the mirrors can literally, it gets a view of the back. If they're on the outside, it can see partially around the back on each side. And it can also see things that you can't see. And so it can make this judgment and then can adapt. Leave it here.